This next unit, we're taking a look at law of sines and law of cosines. Hopefully you are familiar with this, having seen it in geometry and algebra 2. And we are going to entirely focus on application problems for law of sines and law of cosines in pre-calc. So as a reminder of what the law of sines is, in any triangle, not just a right triangle, in any kind of triangle, the ratio of the sine of an angle over the side opposite is equal to the ratio of any other angle and its side opposite. So when we set up our triangle, take a look at how we have angle A across from side A, and then when we set up the ratio, sine of that angle across the side opposite. And same with the other ones. Angle B is opposite side B, angle C is opposite side C. So that's what's important to remember for these triangles. All right, taking a look at our first example. We have a boat sailing along parallel to the shore, and we know the bearing of the boat at two different points. The first thing that I need to clarify is what a bearing is. A bearing is from a north-south, always from a vertical line. So looking at this bearing, the 63 degrees is not the entire angle that the boat makes with the lighthouse. It is the angle that the boat makes with a vertical line or a north-south line. So when we're given the second bearing, same thing. This time we are given an angle, it's just outside the triangle. So the important thing with law of sines is to be able to fill in missing angles, because you're not necessarily explicitly given the angles that you need. So you have to use properties of parallel lines and transversals from geometry, as well as the triangle sum theorem that there's 180 degrees in a triangle. So the first thing that I did was finish filling in this angle that the boat makes with that lighthouse, knowing that that north-south line is perpendicular to the east-west line that the boat is traveling. So I added 90 degrees to the 63 degrees, and I have a total of 153 degrees for that angle. The other thing I did was find the angle inside the triangle at that second bearing. So again, using that north-south line is 90 degrees, subtracting 70 from 90 degrees, I was left with a 20-degree angle. And then using the triangle sum theorem, I was able to get the angle at the lighthouse of 7 degrees. So again, 180 degrees in a triangle. Finally, we need at least one side. We aren't explicitly given how far the boat traveled. We are given how fast the boat was traveling and how long it traveled. So we're going to use those to determine the length that the boat actually traveled in that time. So we'll have to do a little bit of conversion because our speed is given to us in miles per hour and our time was given to us in minutes. So converting that 10 miles per 1 hour into miles per minute, we want the hours to cancel, and we want our units left in minutes because we know how many minutes the boat traveled. Of course, there's 60 minutes in 1 hour, so this gives us 1/6 of a mile per minute, and we know that it traveled for 15 minutes, so we are going to multiply our speed by our time, and we get 2.5 miles that it traveled in 15 minutes. Next, we're going to set up a law of sines. Before we can find the distance of the boat to the shore, which is this length here, we need to know at least one side in this right triangle. Well, the side that I can find most easily, because it's inside the triangle we've been marking up so far, we can use law of sines to solve for this side, the hypotenuse of the right triangle, and then we can use SOHCAHTOA to find that vertical distance. So I'm going to start by setting up our law of sines. So sine of the angle, 153 degrees, over the side opposite it, which is what we're looking for, equals sine of 7 degrees over the side opposite, the one we just found, the 2.5 miles that the boat traveled. Using cross products, we get y times the sine of 7 equals 2.5 times the sine of 153 degrees. So when we divide both sides by the sine of 7, we get our y value is about 9.313 miles. Okay, so that's the hypotenuse of the triangle. The next thing that we're going to do, scrolling back up to look at that picture here. So now that we know the hypotenuse, we can solve for that distance using cosine. We know that that angle inside the triangle is 70 degrees. We're looking for the adjacent, that vertical distance, and we know the hypotenuse. So cosine of that 70-degree angle equals the adjacent, or the distance to the shoreline that we're looking for, over the hypotenuse, which we just found to be 9.313. Multiplying both sides by 9.313, we get that the boat is about 3.185 miles from shore.